Welcome to the part 3 of artificial neural network. So this is the example we are right now working on. In this video, we are going to look at the backward propagation. The previous video we saw the forward propagation. One thing we need to remember is we are just going through forward propagation and in this one backward propagation with one example. So what it means is that we are taking just from the data set, we are taking one example and we are running through forward propagation, backward propagation. That's what it means. So let's look at backprop, how it works. So we need to calculate cost using cost function, right? So this is the cost function, cos 1 by m sigma of minus yi log p41i, because here in our example, the p41 is the output layer, right? So 1 minus yi and log 1 minus p4i, p41i. This is our predicted value, right? And yi is the actual value, right? And this formula comes from the log likelihood of binomial distribution. We have covered this in our logistic regression video. You can just go and look at that to understand how it works, or you can also find the online reference for this. Very simple, no rocket science here. So we need to minimize the cost. That's the whole purpose, right? For this whatever model we build, we want to minimize the cost, right? That's the whole purpose. So that's what we are going to do in backprop. So we need to calculate how much each node in all the layers has contributed to the error, right? So then we calculate the total gradient. So first we calculate the error contributed by each node, and then we calculate the total gradient, and after that we update the all the parameters, like betas, gamma, alpha, thetas. So these are parameters, coefficients or weights, what do we call them? So we need to update them, right, to finally reach the optimum value so that the cost is minimized. So we look at some like sigmoid gradient and error terms. Why sigmoid? Because we have used sigmoid as our activation function. So to calculate the error terms, we need to take the gradient of the sigmoid function, right? So this is how the gradient of sigmoid function defined. So this is gradient of sigmoid function, and this is sigmoid function fx. So fx into 1 minus 1, 1 minus fx. So sigmoid into 1 minus sigmoid is the gradient of sigmoid function. So we need to calculate error terms for each node, right? So error term for output node is nothing but simply we calculate the probability. This is the probability 0. In our case it was p41, right? And we subtract the actual value from that. That gives us the error term for the output node. So error terms for nodes in hidden layers are defined as, so this is how we define, right? So this delta L is the error term for that node, and theta L is the coefficient of that particular corresponding to that node of that layer. L stands for layer here. And then this is the error term from the next output hidden layer, right? So we are calculating the error terms for hidden layer L. So to do that, because it's a backprop, we are going backward. So we need the error term from the next hidden layer. So that is why it is L plus 1. And this is the gradient of sigmoid, right, of the same layer L. And theta L is the weights between layer L and L plus 1. This is what it means. So we look at it with the same example how it works. So let's calculate the error terms for this third hidden layer, right? It's a back prop. So in forward prop, we go from input, then hidden to output. In back prop, we go from output to the last hidden, and then we go back to the input layer. This is how we do. That's why it's called back propagation. So let's calculate the error term of first and second node of third hidden layer. There are only two nodes here, right? So let's look at so the formula. So this is our error term for this node, right? 3 stands for third hidden layer, and 1 stands for the node number, so which is this. So alpha 1 1, this is our so what happens is, what we do here is, whatever error we got in the output layer, right? So that error has been passed on by all the hidden layers or all the nodes from the previous hidden layers, and then that all those error terms have contributed to the error term of this output layer. So when we are doing the back prop, we are this sending back. It's just an intuition. We are distributing the error term back to those to find out what is the actual error term contributed by each node. And what we do is, how we do it, we multiply that by the weight, right? So it is weighted distribution of this error term back to the previous layers. That's how each layer will work on. So what we are doing is we calculated the error term of this, right, which was delta 4, right, multiplied by alpha, the weight, corresponding weight for this node. So this is what we do, and then we take the gradient of sigmoid of this one, right? So it was L31, right? So this was P31 was the sigmoid activation of this node, and then if you take the gradient, it is sigmoid into 1 minus sigmoid. So this is the gradient of the sigmoid of this node, it's P31 into 1 minus P31, and this is the weight, basically error term of this one multiplied by the corresponding coefficient. So this is the simple formula. So then we get the error term for this node. Now same with this. What we do is, again we take the error term of this, which is delta 4, multiplied by the corresponding coefficient for this node, alpha 21, and then we take the gradient of the sigmoid of this one, which was P32, into 1 minus P32, right? So this gives us the error term for this one. So likewise we do it for this. Now third, this was third hidden layer, now the second hidden layer. So you will see the error term for all the nodes. You see what we are doing now. Here we calculated the error term for this node, right? So we will use that, and what we will do is, but see, in this case there was only one node here. In this case, for this layer there are two nodes this side, right? So how we do that? Nothing but just calculate the error term for this one corresponding to this, and error term this of this one corresponding to this, and add them together. That's all we do. So you see, this is what we have done. We have added here, right? And whole thing is multiplied by the gradient of sigmoid. Same like this. Only thing is, this has become, now there are uh, two nodes here, right? Here it was one node, here it is two nodes, and therefore we need two such terms here and add it together. So now we are, so the error term of this is your delta 31 multiplied by this gamma 11, right? Then we send this back to here. Then the error term contributed to this by this one will be like the error term of this one, that is delta 32, okay, and then gamma 12, right? This will be multiplied here and then added together. So both added together, and then we multiply that by the gradient of this sigmoid activation here, right? So which was P21. So gradient would be P21 into 1 minus P21, right? This is, we're just following the formula, right? Now we do the same thing for this node now, right? We are calculating the error term for this one, delta 22. Again, multiply the error term of this multiplied by this coefficient, which is this, error term of this multiplied by this coefficient, which is this, and then added together, and whole thing multiplied by the gradient of sigmoid function of this, which is Pt2 into 1 minus P22. That's all it is. Same thing we do for this one to calculate the error term for this. Again, error term of this multiplied with the coefficient, right? Error term of this multiplied with the coefficient, and we add them together, right? And then the activation, the gradient of activation, which is sigmoid, gradient of sigmoid, which is P23 into 1 minus P23. That's all we do. So it's very simple formula. It's not a big deal. Now we do the same thing, the error terms we calculate for the previous layer now, right? Now we are going to do for the first hidden layer. So first hidden layer, right? All the nodes, you see, beta 11, right? This is beta 11. So error term of this, which we calculated in the previous slide, delta 21, right? For this one, delta 22, for this delta 23. So multiply this error term of this by this coefficient, right? This is what we do. Then multiply the error term of this by this coefficient, which is this. Then multiply the error term of this coefficient, this, and then with the coefficient, and we get this term, the whole thing added and then multiplied by the gradient of sigmoid activation of this, which is P11 into 1 minus P11. We do this same for this node, right? We do the same thing for this node. We do the same thing for this node. We do the same thing for this node. We do the same thing for this node, right? So we are calculating error terms for each node one by one. Now, how to calculate? So we don't calculate the error term for the input layer, So only starting from first hidden layer to the last to the output. So let's look at how to calculate the gradient, right? So we look at the example of this one, right? Input layer and the first hidden layer, right? So what we have done is we have run the forward and backward propagation for one example. Example means one example at a time. That means data set has, let's say, 5,000 rows. So we have run each row one at a time. For forward propagation for first row, then backward propagation for the first row, and while doing backward propagation, we have calculated the error terms for each one of them. So for now there are 5,000 rows, so 5,000 error terms will get for each node, right? So what we need to do is we need to add all those 5,000 error terms for each node. So we get the accumulated uh, gradient. What we get is the accumulated gradient. That accumulated gradient becomes our gradient. So run both forward and backward propagation for all the examples in a for loop, right? To get the accumulated gradient, right? So let's say for thetas, okay, so we are just taking the example of theta. So how to do this? How to calculate the gradient actually? So what we calculated was the error terms, right? Now to calculate the gradient in each example, what we do is we multiply that particular, let's say the error term in the first example, the error term was delta 11, I stands for example, the row number, right, in the data set. So I goes from 1 to m. If there are 5,000 rows, then m is 5,000. So in the first example, what we saw when we went first example, we went forward propagation and backward propagation. So we got delta 11 and 1. This is first example, right? So what we do is we multiply that with, now this has four coefficients, right? 1, 2, 3, 4. So it has four coefficients or weights or yeah, weights corresponding to four input variables, right? So that's why we have four examples, x1, x2, x3, x4. See, we are getting four gradient values here. One thing you need to remember is the total number of gradient values must be same as the total number of weights. So for this node, there are four weights, between this node and input layer, right? So there are four weights. That means we need four gradient values also. They have to match. So what we do is first in the first example we calculated delta 111. This is our error term for the first example, right? First iteration. Then we multiply that x1 value, the first example of x1 value. So we get gradient value, right, for the first example. So these are like four operations. If you see, four different operations. This into this is one, this into this is second operation, this into this is third operation, and this into this is fourth operation. Just to save the space, I have given this notation, but actually you can write separately. This sigma, then delta 11i into x1i. Okay, this is comma 1. Then again this sigma delta 11i into x2i, then again comma. So to save the space, I have given this notation basically. So what you do is you calculate this x1 1, the first example, delta 1 1 1, the first example, right? Then calculate for the second example, this becomes 2. Then third example, and then we keep adding them. So we get the value, the gradient value for this first coefficient for all when we run the example, all the examples, right? So this is accumulated gradient. Now we do the same thing for x2 also. Now x2 is here and this one, right? So there is a gradient here, right? Sorry, the coefficient, which must have been theta 2 1, right? So theta 2 1. See, this was for theta 1 1. Now this is for theta 2 1. So what we do is we have this error term here, right? That is delta 1 1. First example is 1, then x2 1, multiply. Now we go to the next example. Delta 1 1 2, x2 2, and we keep adding them. So we get accumulated gradient for this weight. Same for this weight. Same for this weight. We keep repeating that process. So I have done that. See, for this example, for this node, next node, right? So we did this for first node, so we got 4 gradient values for 4 weights. Now second node in the hidden layer or first hidden layer also has 4 coefficients for again the 4 examples here, 4 I mean independent variables. So again the formula remains the same, only thing the error term will change, right? This was the error term for the first node, this is the error term for the second node, this is the error term for the third node, right? Then this is the error term for the fourth node, this is the fifth node, and then we have sixth node, right? Sixth node, right? We are doing the sixth node here. So we get all the thetas, gradients for all the thetas, right? So how many thetas are there? 4 into 6, 24 gradients, right? So each one is giving us 4 accumulated gradients. So 4, 4, 4, 4, 4, 4. So we are getting 24 gradients for 24 coefficients. That's how it works. So we'll go to the next example where we are going for the second and hidden layer, first hidden layer and second hidden layer. So now we are calculating gradients for betas. It's going to be the same, nothing different. So now the error term for this one is delta 2 1 I, right? The input value of this one is, it's not x but it is probability, right? Sigmoid function, right? What we calculated. So it is p11 I. So first example will be delta 2 1 1 p11, and this is also 1. We multiply that, right? Then when we run the second example, when we run the forward and backward propagation, we get a different error term for this one, right? That will become delta 2 1 2 and p11 2, and then multiply. So we keep adding, and we get one gradient value here, accumulated gradient value for this coefficient, right? Then for this one, this is like it becomes p2, right? p12, right? So then we get another accumulated gradient for this coefficient, like this, then like this, like this, like this. So each one is giving us 6 values here, right? Because here the input layer, this second hidden layer becomes, first hidden layer becomes input layer for this one, right? So again we do the same thing for this node now, right? So again we get 6 different gradient values, right? For this third one we get, again we get 6. So each of the above formula gives us 6 gradient values, accumulated gradient values for their 6 weights, right? Because this has got 6 weight for 6 inputs, this has got 6 weight for 6 inputs, this has got 6 weights for 6 inputs. So there are total 6 into 3, 18 weights. Therefore, we must get 18 gradients. That's what we are getting, right? 6 here, 6 here, 6 here. That's what we are doing. Now we do the second hidden layer and third hidden layer, right? We do the same thing. Now we are doing it for gammas. These are all gammas, right? So again, you see the first node, right? So we get this delta 3 1, right? P21, P22, P23. We get 3 values here, right? Then for this one again, right, delta 3 2, right? So P21, P22, P23, right, for I. So each time we run the propagation, forward and backward propagation, and then we do it for all the examples and take the accumulated value. So each of the above formula gives us 3 gradient values, right? 3 gradient values for 3 weights. So this has got 3 weights, this has got 3 weights, so 3 3. So 3 into 2, right? So there are 6, right? There are 6 weights, right? 1 2 3 4 5 6. So we need 6 gradient values for 6 weights. We do it for the last one also, right? Here, since there is only one output, we have only 2 values, so we'll get 2 gradients. That's what. So this is what I was talking about, that instead of showing like this is just to save the space, but actually it should be written like this, right? So delta 4 1 into P31, right? So this gives us one gradient value for this one. For this one, delta P4 and then 41 and then P21, right? So we get 2 values here, right? So Like this, we could have represented all this and also in the previous example, but just to save the space, we have done it like this. So the above formula gives us two gradient values for two weights. So let's look at how to update the weights, right? Once we have calculated the total gradients for each of the weight, we need to update the weights, right? So this is the formula we follow, right? Update weight is equal to weight minus learning rate into gradient. So gradient we have seen how to calculate, right? What is learning rate? Learning rate is a basically a tuning parameter, while gradient decides, like, the overall updating of the weight, but learning rate decides, like, how fast, like in gradient it's called gradient descent, right? So it is descending, like, so the curve is like this is your cost function curve like this, and we need to reach the lowest point, right? And gradient is basically a partial derivative of the cost function with respect to theta. Theta is the weight. So it gives us the slope. So wherever the slope is 0, that is the global minima, right? That's what. So our curve is like this, and it is going down like this, like this, like this. It is reaching. If it is this side, then it will come like down. So that's why it's called gradient descent. It goes down. But the how large or how small the steps of this gradient would be decided by learning rate actually. At what speed the gradient is moving towards the global minima, so that's what learning rate decides. So depending, usually it varies from 0 to 1, like 0.1, 0.2, something like that. So if it is too large, then the movement of this gradient, going down, it may miss the global minima. It may jump over the global minima. If it is too big, if it is too small, then it may take a lot of time to converge. That's why we need to decide, basically what is the optimum value of learning rate for this gradient descent. So we look at just one example here, right? So this is the, like, learning rate for learning rate, and this is uh, your uh, your gradient, right? The accumulated gradient for the first node, right? And then this is for the second node of the hidden layer. This is for the third node, right? Third node of the hidden layer, and this is for the fourth node of the hidden layer, right? And this is like the fifth node of the first hidden layer. This is the sixth node of the first hidden layer, right? So we repeat the same process. So here is what we just went through, right? So this is the first hidden layer, and these are all our the input layer, right? So if you see, this is what is happening. So this one is related to this. So this is connected to 1, 2, 3, 4, 4 input. So we have got theta 1, 1, then theta 1, 2, 1, theta 3, 1, theta 4, 1, right? Minus learning rate into that gradient. So gradient also has 4 values, if you remember, right? So then we multiply, and each will be deducted from this. So respective values. We do the same thing for this node, this node, this node, this node, this node. So we calculate, so we update each theta value, right? Here, so they are 24, so 24, so 6 into 24 into 6, that is 24. So we update, we repeat the same process for betas here, then gammas the next, and then alpha in the last. So this is the simple way to do it, right? So how does this work? So what we do is there are two for loops, right? So we'll look at it how it works. So we'll go in a for loop first, and then we'll look at this for loop. So this is the for loop, right? The number of examples, right? We ran the for propagation for example I, right? I goes from 1 to m. M is the total number of rows in the data set, right? So in this for loop, we are running the forward propagation for each example, then backward propagation for each example, right? Then we keep accumulating the gradient for each example, right? That's what we did. And then what we do, then we update all the weights, right? So we come out of this for loop. So in this for loop, for each example, we are running forward, then backward propagation, then accumulating gradient at each example. Once we have done this, then we update the weights, which we saw on the previous slide. Then we calculate the cost, right? And then we keep plotting. So these three, this for loop, this runs in this big for loop. Now the number that I provided is just an example, 400 times. It could be 1,000 times, 2,000 times, depending on when you reach the global minima, the cost minimizes, right? So when you plot, it should go down. The cost should go down like this, and it should reach the minimum point. The moment it start rising, that means that it is now diverging, right? So this is what we do here, and it's very simple. So usually in R or Python or any other software, you don't run all these algorithms step by step. There are frameworks, big frameworks like you have in Python, you have Keras and TensorFlow and all that. So you don't have to do anything manually now. There is optimizer also. That optimizer does the even if you're writing cost function and gradient function, that optimizer will do this step for you. It will automatically do the whole thing. It's very fast. Or mostly nowadays we have this framework, so you work on those frameworks, use them to build a neural network or anything like that, or deep learning basically. So thank you so much for your time. I hope you like this video. Please like, share, and subscribe.